All right, so far in our COVID adventure, we were dealing with two kinds of people. One, which is the proportion of susceptible people. So the sus people who are exposed to COVID, and we call this X. People. And Y, which is the proportion of infected people. So those who actually have COVID. And then there's also the recovered people, but at least for now, we don't care about that because we can solve it in terms of X and Y. And then what we got was the rescaled model, COVID model. Again, we define a new unit of time where everyone recovers in 1 unit of time. And we got the following system. X prime is minus Roxy, so minus R0XY, and Y prime is Roxy, so R0X times Y minus Y. And we saw there's a particularly nice interpretation of R naught because R naught is the damage a sick person causes. In other words, it's the number of people a sick person infects while they're sick. While they're sick. And you will see it'll be very useful to consider the cases where one sick person infects either no one or at most one person, and where a sick person infects 2 or more people. So that will be the good case and the bad case respectively. And now, as usual, let's find and classify the equilibrium points. Points, meaning set X prime and Y prime 0. So what we end up getting is minus Roxy equals 0 and Roxy minus Y equals 0. But R naught a priori is a positive constant, so we can cancel this out and we end up getting either X is 0 or Y is 0. And for the other one, we can factor out Y, so Y R naught X minus 1 equals 0. So let's do two cases. One where X is 0. So no one is exposed to COVID. Then the second equation becomes Y times R naught 0 minus 1 equals 0. So this gives you minus Y is 0. And so Y is 0. Which would give you the equilibrium point 0, 0. On the other hand, let's do Y equals 0. So no one is sick. They might all be exposed to COVID, but no one actually has COVID. And then the second equation becomes 0 times R naught X minus 1 equals 0. So 0 equals 0. Okay. And notice this is true no matter what X is. No matter the value of X, So in fact, in this case, the equilibrium points are of the form X comma 0, where X is arbitrary. So it's interesting. Turns out we have a whole line of equilibrium points, namely the x-axis. if you wish. And notice we can actually compare those two. So it turns out case 2 includes case 1 if you let x equal 0. So note case 2 includes case 1. Case if you let x equal 0. And so really the epic conclusion is that the equilibrium points are x comma 0, where x is really arbitrary. So equilibrium points so let me rewrite this. Equilibrium points, which is x comma 0, where x is arbitrary. So that's first of all. And now let's classify them. So again, the yassification here. Yassification. So let's calculate the gradient. So the derivatives, partial f xy is the gradient. So here you differentiate the hell out of everything. So partial minus Roxy with respect to x, partial minus Roxy with respect to y, and I think partial Roxy minus y with respect to x, and partial Roxy minus y with respect to y. So this simplifies, luckily. That's why, so I think we get minus Roy and then minus rocks. Like this course, it rocks, hopefully. And then Roy, no, just Roy, I believe, R-O-Y. And I think rocks minus 1. Minus 1. So that is at every point. And now we need to do it at the equilibrium point. So partial f x comma 0. So this becomes, so you just let y equals 0. So minus rho, like kangaroo, minus rocks, rho, so r0, 0, and rocks minus 1. So in the end, we get, again, partial sleigh. So gradient of f x0 is 0 minus rocks 0 and rocks minus 1. And the nice thing is, so this is once again an upper triangular matrix. So of the form star star 0 star. And remember, if it's upper triangular, we can just read off the eigenvalues. So upper triangular. So here, the eigenvalues are lambda equals 0. That's sort of neutral. And lambda equals rocks minus 1. Now, you would be tempted, according to our list, to just say that it's neither stable, unstable, or saddle. But in this situation, I mean, it would be bad to just give up. So actually, let's explore this further. So, okay, we have the 0 eigenvalue, but now let's look at the sign of rocks minus 1 to get more information. And for this note, When is that 0? So rhox minus 1 equals 0 if x equals 1 over r naught. So in particular, our eigenvalue, lambda, which is rhox minus 1, if x is less than that value, it's negative. If x is less than 1 over r naught, and positive if x is bigger than 1 over r naught. So this eigenvalue is attractive to the left of 1 over r naught and repulsive to the right of 1 over r naught. And that's why actually we can say, again, the 0 eigenvalue doesn't matter here. So our equilibrium point, x naught, is stable if x is less than 1 over r naught and unstable if x is bigger than 1 over r naught. So that is our conclusion. Very good. And now we can analyze this if you want a little bit. So again, if you want to draw a little picture, again, this is 1 over r naught. And really to the left of 1 over r naught, things are stable. And to the right of 1 over r naught, things are unstable. Unstable. And the question is, will we actually see this? So will there be an unstable phenomenon? And here it really depends on whether r naught is less than 1 or r naught is bigger than 1. Because the thing that helps us is note x is a proportion, so actually x is between 0 and 1. And so here now I would like to analyze this, and we can talk about the good case and the bad case. Okay, in homage to one of my favorite shows, The Good Place. So first, let's do the good case, where r naught is less than 1. And I like to remind you, this implies 1 over r naught is greater than 1. And again, this is the good case because we will never see the instability. Because remember, x is between 0 and 1. And maybe here we have 1 over r naught. And really, everything to the left of 1 over r naught is stable. And you can actually show, and this is in the notes, that solutions behave like this. You might start somewhere, but eventually you go towards this axis. Like this, and even like on this axis, that's what happens. And again, the interpretation is, this is the good case, because no matter where you start, solutions will eventually go towards this axis. Will eventually go to x comma 0. And remember, x comma 0, that's good because no one is infected. So y equals 0, no one is infected. So in the end, eventually, no one will be infected. And in particular, what's useful here, there's no sudden rise in infections. So nothing is going up. No sudden rise in infections. On the other hand, let's look at the bad case. Where r naught is greater than 1. So remember, on average, a sick person infects more than one person during their lifetime. So in this case, 1 over R naught is less than 1. And in this case, we do see the instability. So this is X, 0, 1, and then we have 1 over R naught, where on the left it's stable, but on the right it's unstable. Unstable. And in this case, you actually do have a sudden rise in infections. So you can actually show, and again, once again, the details in the notes, that solutions go up and then eventually go down. Kind of like this. In particular, again, you might have no one infected at first, and then suddenly people get infected, and eventually, things calm down. And in this case, when the solutions go up, that's what we call an outbreak. So let me summarize. So if R naught is bigger than 1, so if R naught is bigger than 1, then we have outbreaks. Outbreaks where, again, Y, which is the proportion of infected people, suddenly increases. Even though eventually, according to our model, it will decrease. Eventually, Y decreases. Where, again, we have no outbreaks. The last thing I want to mention is actually about the effect of vaccines. And the question is really, when are we in that stable region? So effect of vaccines. Vaccines. Okay. So when is X less than 1 over R naught? When are we in the stable region? And for this, we need to actually define the number of recovered people, or the proportion of recovered people. So Z is R over N, which is the fraction of recovered people. And here is a very easy criterion that guarantees that X is less than 1 over R naught, that we are in the good region. So fact, if Z is greater than 1 minus 1 over R naught, then X is less than 1 over R naught. And the proof of this is in the notes if you're curious. But more interestingly, let's talk about the interpretation of this. So, in other words, if enough people have recovered or are immune to COVID, then we are in the good region. So if enough people are vaccinated, really, vaccinated, then we're stable. Or in other words, we have herd immunity. So in other words, at least according to our model, vaccines, they're not a bad thing. Okay, they do guarantee that we're in the stable region. And the question is, are we in that case? So do we have herd immunity right now? So let's compare this with real data. So comparison with real data. So I got this info from the New York Times. So New York Times data from spring 2020, which estimates that a sick person infects 3.8 people on average. So which tells you that 1 over 1 minus R naught is roughly 74%. So in other words, we need at least 70% of the population to be vaccinated. And the question is, are we there yet? Well, last time I checked, so current data, so last time I checked, it seems that only 69% of people is vaccinated. At least in the US population. So unfortunately, we're not quite there yet, but almost.